Testing, testing. Hi, my name is Zhang Yue, and today I'm going to have an explanation of the solutions to assignment 2. Before we start the explanation of our solutions to assignment 2, I summarize some background knowledge we should know before we deal with such problems, which is delta method, central limit theorem, and maximum likelihood estimators. Okay, now we move to the problem 1. I will lead you to read this problem and show some clues that what method we should use and how to use this method. Okay, in the problem A, we can see that we need the estimator of theta, which is defined by a nonlinear equations of mu. In this problem, mu is unknown, and we need to think of to use the delta method here. And I also listed the first order delta method here in the behind the problem. Okay, maybe we can just use these equations. In the problem B, and say that we also need to find the estimator of theta, which is defined by a nonlinear equation of sigma. And in this problem, sigma is unknown. So we also need to think of to use the delta method and maybe it's have some difference between the problem A. We can see the bottom equation here. Okay, for the problem A, can I separate this in 4 steps? In the step 1, using the results from the maximum likelihood estimator, we can have this conclusion. Maybe you forget how we can get this conclusion. I post the process here, and maybe you can check this after our class. Okay, let's move back to our solutions. For the step 2, we know that xi follows the distribution in mu4. So xn bar follows the distribution in mu4 minus n. So we know that from xn bar follows this distribution, we can have this. Okay, have this function in the bottom of step 2. So it's very similar, right? It is very similar to this function, right? So we can apply in the delta method, and we define G mu equals to this function, which is show in the it is the definition, right? So we have this function here. It is this function, right? We just use this first order delta method. So in step 4 by CLT, we have okay, since we need to use this information, and we should make a transformation to transform the J and the such equations to N01, which is a standard. Okay, so it's standard. And so we can have this functions here and make a simplification, which is equals to the 96%. And substituting the estimator of mu by Sn bar and this information, the 96% confidence interval for theta is this. So we are done this problem. Okay, let's move to the problem B. We notice that sigma square is unknown. Then this function, which is a CLT, right? CLT scenario will be shows in the CLT scenario will be more random. So we cannot use this scenario in this problem. What can we do to deal with such problems when the sigma is unknown? I post the equation here. Is okay. Oops. Okay. We need to use this equation to deal with this problem. So in step one, we use the Sn-1 equation here to replace the unbiased to be the unbiased estimator of sigma. Then the estimator of sigma is here. Of theta is here, right? It's a definition, right? So by chi-square distribution, we can have this, and we can find the variance of Sn-1 square equal have this function here. So in step two, we define JSN-1 square equals to this function, which is based on the definition of theta. So now we apply the delta method I showed here. Okay, I showed here. So we can have this after the simplification. Okay, for the step four, in the step three here, and we know the variance of Sn-1 square, so maybe we can so then we can have the standard standard estimator of theta, which is this standard oops since if we want to use the information shows in the problem give us, we need to transform it into N01, right? Here we do this we plus the SE theta here. So we can have this function here. So which is equals to the 96%, and so the 96% confidence interval for theta is this. So we are done this problem. Okay, let's move to the problem 2. Okay. It is maybe much easier comparing with the problem one. So by central limit theorem, we can find that xi follows the distribution in mu1. Then we can do the scenario to transform Si minus mu into the standard normal distribution in 0, 1. So we have so we want to find Pyi equals 1 because we want to find the likelihood function. So we need to find Pyi equals 1, which is equals to Psi bigger than 0 here. So we have this function, and this is quite similar. Psi minus or equals to 0. We can think of the CDF of the standard normal distribution, right? If we know the CDF of standard normal distribution, we can have a concrete number. So we finally have this solution by mu. If we know what mu is, we can really know the solutions, right? So as same as Pyi equals 1, we can have Pyi equals to minus 1 here. So which is equals to 1 minus 5 mu here. So now we can deal with the likelihood function is we have 4 data, which is let me check, which is bigger which is positive, and 6 data is not not positive here. So we can have the likelihood function there. Now applying the MLE, let's this equals to log, and we make the first derivative equals to 0. Then we have phi mu equals to 0.4, and the estimator of theta equals to phi mu equals to 0.4 here. And for the problem B, from A, we know that phi mu equals to 0.4. Then the estimator of mu equals to the inverse function of phi 0.4. And we can check which is about equals to this. So we are done this problem 2 here. Okay, for problem 3, the problem A, we need to find the mean and variance of x. I think that's quite easy. We just put this in the the functions ex and variance x here. I posted this here. So we can have the mean of x is 2 minus 2, is 2 minus 0 theta, and variance is here. Okay, and for the problem B, from the weak law of large numbers theorem, we know that xn bar will approach to ex, which means equals to this. It is the conclusion we get from the problem A, and we define J as n bar equals to this. Okay, which is defined by this estimator as n here. So by the continuous mapping theorem, we can find that J as n bar per to theta. Then we have the estimator of theta, which is converges to the theta. Okay, for the problem C, from this 10 data, we have S n bar equal to this, and theta, the estimator of theta n equals to this. This is from the definition of B, right? So we have these two numbers. And we define J as n equals to this. So we have the derivation of J as n bar. And now we can apply the delta method is quite similar with our solution in the problem 1A, right? So it's quite similar. So we also have this equation where the mean ex equal to this. So we applying the delta method we mentioned before. So we got this. Then we make some simplification. Okay, so we also need to transform it into the standard derivation. N01, and we can use this Z 0.025 here. Okay, now make a simplification here, and we are substituting the estimator theta n equals to 4 minus 7, right? So we get the 25% cell of theta is here. So we are done this. And for D, how we explain the interval guides found in C for theta. I think the interval guides found in C for theta means that the possibility also we call it confidence is 25% that the true value of theta lies in the interval we got from C. So these are all the solutions of these 3 problems. Okay, so goodbye.